All right then, so there's our element, and there's the stresses on our element, right? Now we want to represent the state of stress graphically using Mohr's circle. So let's just work our way through our steps here, right? The first step is the center of the circle. What is the center of the circle, or the coordinates? Well, that has coordinates sigma, average, and 0, right? Well, sigma average is equal to sigma x plus sigma y over 2, which we've seen this already, right? We've worked this out. It's minus 12.15 newtons per millimeter squared. Now, I am going to, I am going to work out or next. Now, what did I say step 2 was up here? Step 2 was locate the center. Step 3 was locate point X. Now, before I actually locate point A, I'm actually going to want to plot this circle. Now, I'm going to plot this in Python, right? So I'm going to want the X and Y Cartesian coordinates of this circle. So the first thing I'm going to do is work out what's the radius of the circle. And I can just plug my numbers straight in to the expression that I have for the radius. The radius is 22.67 newtons per millimeter squared. Now, as I said, I'm just going to do a little aside here, because this is only really necessary if you're plotting this and you want the XY coordinates. So I'll just say plot my circle, and I just want to plot a set of X and Y values, which means I'm going to want to get the Cartesian coordinates of the circle. All right, what does that really mean? Well, my circle is this here, and any point on that circle we can identify with an angle theta, and I know what my radius is, and so that point has Cartesian coordinates. We'll just call it xy. That's what I'm going to plot. Now, x is going to be or times the cosine of theta, and y is going to be or times the sine of theta. That assumes that the center of the circle is at the origin. We know the x coordinate of the center of our circle is shifted over, so we need to remember to add on sigma average onto this here. So this is how I'm going to actually plot this circle. All right, let's jump back over to our notebook, and we can actually plot this thing out. And then we're going to jump back over into this notebook, this handwriting notebook here, and finish out the question once we've plotted our circle. It's not strictly necessary, by the way, to go ahead and accurately draw or plot this circle. You can sketch the circle out. It's just I want to have a nice, clean, accurate plot to work from as I'm explaining this. All right, so let's go ahead and plot this thing. So we want to define sigma x, sigma y, and tau xy. In fact, we have definitely done this already. So let me go to wherever I did that before. Sigma x, sigma y, and tau xy. Let's take those and bring them down here. Again, just to emphasize, you don't actually have to plot this in Python. What I'm trying to say is it doesn't have to be accurately drawn. You can work it all out from the geometry of the circle, from just a sketch. But as I say, I'd like to have something nice to work with here. So the first thing I want to do is calculate sigma average, sigma x plus sigma y. All right then, now I want the radius of the circle. Now we want theta. Now what's theta going to be? I want a range of theta values, because again, I'm plotting a circle, right? So I want, from the NumPy library, I'm going to take a range, which is just a function from the NumPy library. That's going to give me a range of numbers. I need to pass it in the lower number, and then the upper limit number plus 1, right? Just one of the peculiarities, right? So I want a range of values from 0 to 360, which means I have to pass in 0 and 361 here. Okay, so this is my range of angles in degrees. Now I'm going to want that in radians, as usual. So theta rad is equal to pi over 180 times theta. Okay, so now what I want to do is generate all of the points that make up the actual circle itself. So I'm going to define all of the x, let's just call it in inverted commas, all of the x coordinates as sigma x1, right? So that's going to be sigma average plus or times the cosine of theta. Again, we saw this over in our notebook. So that's going to be or times np dot cosine. So we're taking cosine from the NumPy library, we're passing in theta rad. That's going to give me all my Cartesian x coordinates. Now I want my Cartesian y coordinates. We'll call that tau x1 y1, and that's going to equal r times the sine of theta. They are all of the data points that make up the circle itself. We can go ahead and plot it now. Just cheat a bit and put some code in here. So what have we got here? This is the usual, define a figure, add a set of axes. This is a new line of code. I want my x and y axis to have an equal aspect ratio, okay, because they're both newtons. The horizontal and the vertical axis are both in newtons per millimeter squared, and so they'll need to have the same aspect ratio if I want this thing to look like a circle. And now I can go ahead and plot the circle itself. So if I want to plot the circle, I can say axes.plot, and all I'm going to do initially is just plot all of my sigma x1 values against all of my tau x1 y1 values and just see what that gives me. Excellent, there is more circle, right? Now let's jump straight to the end where I like to do all of the housekeeping to make it look a little bit better. So let's just plot in, or just add in some axis labels, title, turn on the grid. This little line here is just saving the figure out of this Jupyter Notebook because I want to bring it into my other notebook so that we can actually sketch and draw on it. So let me run that, and we have our axis labels and a nice little grid. So now let's add some additional pieces to this thing. So I'd like to now plot the horizontal diameter next, right? So what's this? We're plotting a horizontal line, right? The line is going to have a set of x coordinates. So it's a horizontal diameter. So it goes from the very left of the circle over here to the very right of the circle over here. So its x coordinate here will be sigma average, the center point of the circle, minus r, and then this is going to be sigma average, center of the circle, plus r. So there are my two x coordinates, and its y coordinates are going to be 0 and 0. It's going to be a dashed red line. There we have it. So that's our horizontal diameter. Let's plot in our vertical diameter. Okay, so again, we're going in the x, so the x coordinates are going to just be sigma average, the center of the circle. And now this is going to go from minus r, remember the y-axis is positive downwards. Have I actually coded that in yet? Ah, there we go. That's an important line actually, which I didn't actually mention. You see this line here? This is where I am inverting my y-axis. So I'm saying axes, invert y-axis, and that just makes all of the downward values positive and the upward values negative. Okay, an important little point I glossed over initially. So now we are plotting in a vertical diameter. Let's run that guy. Okay, there we go. So obviously there's the center of our circle. Let's just plot in a little point there just so we can visualize that a little bit easier. So I'm plotting in a single data point with x coordinate sigma average and y coordinate 0, which is the center of our circle. So let's do that, and there we have it. So there's more circle. Now you can look at this before we do anything else, right? You can look at this and you can say to yourself, right, well, straight away, if the horizontal axis is the normal stress axis, right? Well, the maximum value of normal stress happens to be right there, okay? There's no other larger values of sigma x on the circle, so that must be my principal stress, okay? The maximum value of the normal stress. And this guy over here must be my minimum principal stress, or my, what would we say? We'd call it the minor principal stress. So over on the left is the minor principal stress, on the right is the major principal stress. And then if we go and look at the maximum value of shear stress, that's going to be in the vertical direction. The maximum negative value is up here, and the maximum positive value is down here. So you can imagine if I'd sketched this thing out on paper, once I know where the center is here and I know where the radius is, or what the radius is, I can straight away work out numerically these values. Right, so next we're going to plot point A, right? We're going to plot point A on the circle. So let's go ahead and add a note in here, and the note's going to say plot point A, the stress on the positive x face of the element. Right, so if I just say axes, right, axes.plot. Now what's the x coordinate? It's going to be sigma x, and the y coordinate is tau xy. These are just there, sigma x here and tau xy here. Right, so we're just plotting that data point on in a little marker is going to be a little circle. Marker, face color is green, edge color is black. Let's see what that gives us. Okay, here you have it. That point on the circle represents the state of stress, right? It represents the stresses on that positive x face, right? Now we can go ahead. I'm just going to draw on a straight line that goes between that point there and the center of the circle. No real mystery to this. It's just going to be the x coordinates are going to be sigma x, and then sigma average, the center of the circle. The y coordinates going to be tau xy and 0. It's going to be a green dashed line. There we have it. And now let's plot on point B. Right, so point B is going to give us the stress on the perpendicular face of the element. Plot point B, which is the stress on the positive y face of the element. So again, the coordinates, the x coordinate or the horizontal coordinate is sigma y, and the vertical coordinate is minus tau xy. So we can plot that guy. And you have it there. Look, there's your point there in yellow. Now you'll notice straight away, those two faces on our element are separated by 90 degrees. They're mutually perpendicular faces. But on our Mohr circle, they're separated. The points on the circle are separated by 180 degrees. All right. So that's an important thing to, as I said before, lock into your mind, that relationship. Okay, and let's plot a dashed line. Okay, there we have it. So over here we've got point A, over here we've got point B. Before we wrap up, let's just plot a couple of little markers on here just to identify the principal stresses. Okay, so we said our x coordinate was the sigma average plus or, so which is just sigma average takes me to the center of the circle, and plus the radius brings me to this point out here, and my y coordinate is 0. We're going to use an x there to mark that, and there we have it. So that's my major principal stress. We can plot the minor principal stress just as easily, and I notice my note here is incorrect. That's not the center of the circle. I'm always leaving the wrong bloody notes in. That's not the center of the circle either, is it? All right, then don't worry too much about the notes. So let us copy this. Now I want the minor principal stress, which means it's going to be at sigma average minus the radius. Let's have a go at that, and there we have it. So there's the two positions of the principal stress. Now, importantly, we're going to see it now when we start sketching on top of this thing. But this angle here allows us to identify the location of the principal planes. And I won't dig into that too much now, because we're going to look at that in a bit more detail in a second. Right, now let's plot the positive, max positive and negative shear stress. Right, so that's going to have the horizontal coordinates just sigma average, and then it's going to be plus or. So that's actually going to be this point down here. And yep, there we have it. There, that diamond is representing the shear, maximum positive shear stress, and and that's not the center of the circle again, look. So let's copy that, and this time we want a negative or. Okay, so there is your maximum negative shear stress, maximum positive shear stress, your major principal stress, and your minor principal stress. And of course, with simple geometry, we can work out the angles between this radial line here and all of these other points and all of these other stresses, and they will be, obviously that's going to correspond to the different angles for the principal planes and the planes of maximum positive and negative shear stress. So now that we have this, right, let's bring it back over. We've exported a picture of it. Let's bring it back over into our notebook and start sketching on top of it. All right, then we're on the home straight here. We've got our Mohr circle, and we've identified some key points on the Mohr circle. So the first thing I want to do is just call those out again, right? So what have we got? We had this point here. That point there was point A. Right, so that point corresponded to, or the stress at that point corresponded to, if I just sketch it out very, very small here, if we have our element here, the coordinates of point A are actually the stresses on this face of our element. All right, and so we have a stress here that was going to be a compressive stress of 32.5, and you can look at the coordinate. Here, it's going to be a negative 32.5, and the shear stress on that point is going to be a negative, whatever it was, something like negative 10. So that was going to be, that's a positive x face, and so to get a negative shear stress, I have to have it in the negative y direction. So that's your stress there. So again, the coordinates of that point are simply sigma x and tau xy. The coordinates are the stresses that we started off. We knew the stresses on that face. All right, then what did we do? Well, in fact, before we even got that far, we worked out what the center of the circle was, and that was sigma average 0. Okay, so that's that point there. Where to next? So then we worked out A, and then we identified point B, and point B was this guy down here. I'm not sure that's really the best color. We'll stick with it for now. So there's point B, and point B corresponded to, if I sketch out my element again, point B corresponded to the stress on this face. So you'll notice point A and point B are only 90 degrees apart on the element, but they're 180 degrees apart on Mohr's circle. I know I keep labouring that point, but it's really quite important. So the coordinates of this point are sigma y, and minus tau xy. All right, and of course that's just the stresses on the face that we've already pointed out, and so that was going to be a tensile stress. So it was a positive normal stress, which made it a tensile stress. So that's 8.2. And what did we have? We had a positive shear stress, so that's going to be a stress in this direction. Okay, because you can imagine that is a positive y face, but you can imagine to rotate around to that face, our set of axes would also be rotated. So our set of axes would now be the x1 axis. After you've rotated by 90 degrees, that would be the x1 and that would be the y1, and so that would be a positive, that arrow would be a positive shear stress because it is acting on a positive face in a positive y1 direction. All right then, so that identifies point A and point B. I'm just going to say up here, this point A is theta equal to 0 degrees, and this point down here is theta equal to 90 degrees on our element. Okay, so that is, oh yeah, then what did we do? Then we identified this point here, which was the minor principal stress, and this was the major principal stress, and then we had the maximum negative principal shear stress up there and the maximum positive shear stress down here. Okay, so let's go ahead and work out the numerical values. So let's imagine, right, let's imagine we got here, let's imagine all we knew starting out was these stresses, and we knew that the orientation of our element was 0. Okay, so this was for theta equal to 0 degrees. Let's imagine that's all we knew. Well, then we would come down and we would work out sigma average, right? We'd work out sigma average, and that would give us that guy. And then we'd work out the radius, right? And that would give us that guy there, right? Now, if we were just sketching all this out on paper, you can ignore this this little call out bit here. You can ignore that, because you could sketch all of this out on paper with just a rough sketch of a circle, and you'd be able to identify everything we've identified so far. So then, picking up the story at that point, what would the next thing you would do be? The next thing would be to work out what are the principal stresses using only your circle now, because remember, we've identified the center of the circle and we've identified the length of the radius of that circle. That's all we know. So we can then, and we've got a sketch then obviously, so then we're going to work out what are the principal stresses. Okay, so well, we know the major principal stress is just going to be sigma 1 plus r. Sorry, the major principal stress of sigma 1 is going to be sigma average plus r. And we know sigma average is the center of the circle, which is minus 12.15. The radius was 22, well, I have 22.67. Yeah, 22.67. All right, and that gives us, say, sigma 1 equal to 10.52 newtons per millimeter squared. Okay, that's good. Well, we know that's correct. Again, just really emphasize, what did we know in order to get that? All we knew was the state of stress at theta equal to 0. We then used that information to calculate the location of the center of the circle and the radius. And once we have that, this is the beauty of Mohr's circle. Once you have those two pieces of information for the circle, you have essentially every state of stress, every possible state of stress at that point in the element, because every point on this circle is a state of stress at a given orientation. And that's the key thing. You can then just look at this circle and straight away pick off the key values the same way I just said. Well, that's one principal stress, that's the other principal stress, that's the other shear stress, and that's the other shear stress. And then it's just the very basic geometry of this circle in order to work out the corresponding angles and values. So straight away we've worked out sigma 1. Let us go ahead and work out the angle theta P1 now, right? So the angle theta P1, well, let's see. This angle, remember this green line here, right, that is your reference line, right? So that line is corresponding to theta equal to 0 degrees. Now I need to work out this angle here. all the angle that I need to rotate to get all the way around until I'm at this stress over here. Now we're going to call that angle 2 theta P1. Remember, a rotation of theta on our element is equal to a rotation of 2 theta on our circle. Now, I'm going to then further, just to make my calculations a bit easier to understand, I'm going to call this little angle here alpha. All right then. So, in order to work out theta P1, I'm going to say that 2 times theta P1 is going to equal whatever alpha works out to be plus 180, right? So you've got your 180 degrees plus alpha. Okay, so I just need to work out alpha, which I can do fairly easily. So if I just construct a right angle triangle with the angle in here being alpha, well then this distance here is just going to be, if you think about it, that's just, let me get a different color here. Let's come down here in, that's a rubbish color. Let's come down, that's not a great color either. Let's come down here. Right, we're coming down here, so this horizontal distance here is just sigma x, right, minus sigma average. All right, so that's going to be sigma x minus sigma average. This is why I've been saying, you know, you can use the geometry of this circle. So that's going to be minus 32.5 plus 12.15, which is going to be minus 20.35. And then this is going to be 10. And so we can say that alpha is equal to tan inverse of 10 over 20.35. Alpha is equal to 26.2 degrees. And so I'm just going to come down here and I'm going to say 2 theta P1 is equal to 26.2 plus 180. That's going to equal 206.2. And so theta P1 is equal to 103.1 degrees, which we know is correct. So we've worked this out directly using equations previously. We've worked out this value and we've worked out this value down here. But I like this method because I find it's an awful lot more intuitive. I can look at this straight away and I don't have to worry about remembering equations. There's no transformation equations to remember. All I have to know is the location of the center and the radius. Remember those two things and you can work out every state of stress at this particular point in the structure. Right, let's just finish it out then. So what is the minor principal stress? So the minor principal stress, sigma 2, is going to be sigma average minus R. And again, we can work out our angle this time. This is our angle theta P2, right? So this is the angle I need to move from, I need to rotate from my reference axis, from this reference axis, until I get down to this corresponding axis for the horizontal axis. So what I can say now is that is theta, that's 2 theta P2. I can say 2 times theta P2 is equal to alpha. We already know alpha is 26.2, and so theta P2 is equal to 13.1 degrees. And of course we know that's correct because we've seen that and we've seen that before. So we can then go and focus on the shear stresses. Again, pretty trivial. At this point, tau max is just equal to plus or minus the radius, which is plus or minus 22.67 newtons per millimeter squared. And we use the exact same trick to work out the angles, right? So 2 times theta S1 is going to be alpha plus 90 degrees this time. How is that? Well, this time, let me just get rid of that. This time I'm going from my reference axis down to this axis, right, which is going to be 90 degrees to here and plus alpha to get me to there. So that's my 90 plus alpha, that's where that's coming from. And so we can solve for theta S1 equal to 58.1 degrees, and that means theta S2 is just add on 90 degrees to that. It's 148.1 degrees. 90 degrees on the element or 180 degrees on the circle. All right. Okay then. Do we have everything we need at that point? We do have everything we need, other than just to say, just to note or to observe that the normal stress, the value of the normal stress at when the shear stress is at its maximum, the value of the normal stress, well, we can tell straight away looking at the circle, draw your line down, and it's through the center of the circle. And so the value of the normal stress on the planes of maximum positive and negative shear stress is just sigma average. Okay, so we'll just state it just for completeness. That is all we need to cover, I think, for an introduction to 2D stress analysis and Mohr circle. I mean, you can sort of go through many versions of this type of question, but the fundamentals are always the same. Provided we understand the state of stress on a set of faces, a set of mutually perpendicular faces, and we know what the corresponding shear stress is as well. Provided we have that information, well, we need to do two things, right? We need to work out sigma average, right? And we need to work out the radius. Now, everything we've done up until this point, I would say, is really just in service of getting us to this point, right? I personally wouldn't try to remember the transformation equations and actually try and, execute those transformation equations. If I had to address something like this practically, I would go straight for a more circular approach. I would work out my average stress, I'd work out my radius, I'd do a little hand sketch, of my circle, I'd approximate, I'd work out, okay, well that's the point is somewhere there, I'd have coordinates for that, then I know that I have another point down here, I'd have coordinates for that, and then I would be able to do everything that you saw me do here, right, all of this stuff, all very basic equations and all very basic, basic equations. I would do all that, but instead of having a nice, well-plotted version of Mohr circle, you can do all the very same thing on just a hand sketch of Mohr circle. So in that way, I hope you'll agree that it is a much more intuitive, well, for me at least anyway, I'm a sort of a graphical kind of a person. I find it much more intuitive to understand stress and the stress field at a point through the lens, if you like, of Mohr circle. So that's it. Hopefully you found that helpful. I think we leave it there.